Tired of doing 2 rectangles?
I'm sick and tired of
4 rectangles? Aiden, would you like to do 20 rectangles? You want to do an infinite number? Oh my gosh, did you hear him? He doesn't want to do 20. He wants to do an infinite number of rectangles.
That's not.
Oh my gosh.
Did you actually say that?
Yeah,
he did. Get out of here.
Because he's amazing.
Class pet.
Whoa! All right, here we go.
Teacher's favorite. He is.
I think we're voting to remove something from class.
Yeah, and I wrote Aiden. Great idea.
You get to have one vote.
In the red sweatshirt.
You get to have one vote. And I get 51% of the vote.
That doesn't count. That's cheating. That's not how math works.
This is called a dictatorship. This is not a democracy.
Big math.
I love communism. He thinks we should bring it back. He told us during 6th hour that he thinks we should bring back communism.
All right, here we go.
7th hour.
Sure. So we learned a new symbol today. This is called an integral symbol. An integral symbol. Okay.
Alex thinks we should bring back child labor.
And this means the area bounded under the function from A to B. So those are our bounds. A and B are our bounds. And this is the function. Okay? And then there's a dx at the end. And that's calculus notation. What does it mean? It means this. It means the limit as n goes to infinity, n, of the sum from I equals 1 to n of f of x sub I delta x. Where x sub I is equal to something and delta x is equal to something.
No.
Isn't that beautiful?
No.
Well, you look at that like, wow, that must take something really, 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 really smart to do that. Like, who could actually do that? You must have to be a genius. Yeah.
What is that sign after the?
It's a semicolon. It's used in English.
I was just making sure.
So we're
it wasn't
doing
the fancy
English.
shit. We're doing English.
Okay.
Hear me out.
I'm
We're
not
using
using
commas, periods, letters in our math. I think it just really wants to be like an English class.
I think that you can still drop this class.
I think that then I would be quitting.
All right. So, well.
And Mama didn't raise me.
Mama didn't raise no quitter. All right. I'm going to remind her of that. Suppose you are finding the area under the curve f of x is equal to x squared, bounded from 0 to 4. That's a type of a problem we've encountered before, have we not? Okay. If you're finding the area of 8 rectangles, what's the width of each rectangle? 1/2. How did you come up with that?
4 divided by 8.
Yeah, you said 8. I'm sorry. You said I'm going to take 4 minus 0, and that's going to give me the entire width. And I'm going to divide that by 8. 8 being the number of rectangles, right? Suppose we want to find the area of those 8 rectangles, and we're going to do right-hand sum. At what spots do we evaluate the heights?
Right side.
Okay, so we're going to go from 0 all the way over to 4, okay? We're dividing it into 8 parts. What's the first spot that you evaluate the height? You evaluate it 1/2, and then 1, and then 3/2, and then 2, so on and so forth, right? All the way over until you get to 4. Everybody agreed?
Yeah.
Any question there? We learned that the other day. Everybody confident? Okay, let's move along. Suppose you're finding the area of a curve f of x equal to x squared, but you're just going to bound it from 3 to 4. Okay? If you're finding the area of 8 rectangles, what is the width of each rectangle?
1/8.
How'd you get that?
same thing you did up top.
4 minus 3 divided by 8.
Wait, what did you just do?
So the length of the interval is 1 unit.
Oh, yeah.
And I'm dividing into 8 rectangles, so I get 1/8. Talk to the person next to you. At what values do you evaluate the height of those rectangles? See if you can figure it out. Talk. Go.
4.
Are we also drawing another number line?
And we need David one?
But we're doing this, are we doing this right-handed or what?
Yep.
Okay.
If it doesn't specify, are we assuming it's right-handed?
Yes.
Okay.
Everybody start at 3 and 1/8. Why don't I start at just 1/8?
Because it's not in the interval.
Now the interval starts at 3. Agreed? Good. Okay. So here's where we put it together, and then we will start to execute the task for today. We just have to do one last deep level thinking idea, and then you'll be ready to go. You guys are super smart. Suppose you're finding the area under the curve f of x equals x squared is bound from 3 to 5. You're finding the area of n rectangles. Talk to your partner next to you. What's the width? Go.
2.
5, 4, 3, 2, 1. I have 2 over n. I took 5 minus 3 and I divided it by n. I got 2 over n. Everybody clear on that? Okay, so what that means is as we go all the way to the top, we know now that delta x, it represents the width of our rectangles. Delta x in this problem will always be b minus a, and we divide that by n. Yes.
With your little squiggly thing at the very front of that?
Yeah, it's called an integral.
Okay, what does the B and the A mean? Like,
Those are your bounds. So like we said, 3 to 4, 0 to 4, those are my bounds. Okay, good question. All right, now we come back for the last part. If you're finding the area of n rectangles in that situation, at what x values do you evaluate your heights? This is a little bit more challenging. I'm giving you a minute to think about this. See if you can write down like the first 3 or 4 spots where you evaluate the heights. Go ahead. Think about it. Okay, 5, 4, 3, 2, 1. Let's see how we can use this information. I try to use the previous stuff to help you out. Notice that we started at 3, right? But we didn't go to 3, we went to 3 and 1/8. We went over 1 width, didn't we? Okay, so you start here at 3, and we are going to go from 3, we're going to go over 1 width. What is 1 width? 2 over n. So that's the spot that we evaluate our first height. Then to get to this spot, I go over another width, don't I? So I have 3 plus 2 over n, but instead of going over 1 width, I go over 2 widths.
Would it be the same as like just 4 over n?
It would be 4 over n, and then the next one, I'll go over 3, and then I'll go over 2 over n, and I'll go over 4, so on and so forth, until I go over an infinite number of widths that we divide up into an infinite number of rectangles. Now let's understand what this means in context of this type of problem. We say that x sub I, that's the spot where we evaluate our heights. So to understand what this piece is saying, all you need to understand is that this thing right here, it means the area. That's all it means, okay? And then what this means is we're going to have an infinite number of rectangles. And remember, how did we add up our rectangles in the previous days? We took the what times the what? The width
Times the sum of the.
times the sum of the heights of the rectangle. Everybody remember it? Width times sum of the heights. Everybody got that? This thing right here, delta x, this is the width. What does this big thing right here, it kind of looks like a weird E, what is that? Yeah, it's the Greek letter for S, capital R-S, which means sum. Didn't we look at that at the end of last year? Exactly. This thing means sum. The sum of what? This produces right here the heights. And when you produce the heights, you took your x values and you plugged them into the function. So the last thing we need to decide is, where do we evaluate the heights? Well, you told me that in this scenario, hold on one second, in this scenario, you took the starting point, okay, 3, and you simply added a width to it, right? So as we go through this process, you're going to take the starting point. What's the starting point for our interval in this situation? Starting point for the interval. A. You're going to take A and you're going to add to it a width, which is B minus A over N times I. I being the rectangle number. So if it's the first, second, third, fourth, fifth rectangle, that's how many widths we've gone over. And so those are the pieces that you need in order to accomplish today's task. Question? Hannah Banana.
For the area, is that whole first thing? Or
Yeah,
is it
the
just
whole first thing's the area.
Okay.
Yep, hi.
Is the I a subscript?
I is a subscript. Yep, x sub I. So x sub 1 would be the first spot where you evaluate your height. X sub 2 would be the second spot. And we end up doing an infinite number of those, okay? Because n goes to infinity. So let's accomplish it. We will add up the area of an infinite number of rectangles. This will not be an approximation. It will be exact. Consider the area beneath the curve from f of x equals x squared from 0 to 2, okay? So all I'm going to do is we are going to skip actually evaluating the right-hand sum of 4 rectangles, and we're going to go right to this space. But what I am going to do is I'm going to quick just draw here what our shape looks like. So x squared, and we're going to go from 0 to 2. So I used to have us practice the right-hand sum so we get in the thought again. I just don't think we need that. You guys are a very high-functioning group. You're very intelligent. There's no need to go further with that. Yep. Okay. So the first thing that you do, I'm going to write out what we had on the last page up here so I could just reference back and forth. We said the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. And we'll use that piece in a second here. The problem always starts out with determining the width of n rectangles. The width of n rectangles. So the width of the entire interval is 2. So what's going to be the width of each rectangle? 2 over n. So 2 over n is what delta x is. Everybody got that? Okay. So then we move on to, for what x values do we evaluate the sum? So remember we said that delta x was equal to b minus a over n, and then x sub I was equal to a plus b minus a over n times I. So as you look at this situation, what is our a value? A is just 0. Everybody see we're starting at 0? And then we already determined what b minus a over n is. What is b minus a over n? Just 2 over n. So we just multiply it by I. So we just get 2I over n. Are we okay with those?
So that's like the sum of all.
So we're now going to write the sum of all those things, okay? And it looks like this. We're going to write this same thing, but now we're going to use we're going to use the pieces that we've just laid out. So express the area as a definite integral. So what you want to get used to writing is the integral from 0 to 2 of the function. What's the function? X squared. And then we write dx. We'll talk about what the dx means in a second here. Equals the limit as n goes to infinity of, what comes next? Sum from I equals 1 to n of f of x sub I. That means we take our x sub I and we plug it into our function. So our function is x squared. So what thing do we plug in place of x squared? 2i over n. So we've got 2i over n squared. Times 2 over n. Very important that if you don't understand how I got to this point, that you ask now. We all good? Because if you can get to there, the rest ain't bad at all. The first time through is going to take us a little while, but you're going to get pretty good at this. And do I dare say, there's a lot of people who actually end up really liking the process. It's pretty cool to see how it works out. I don't know how to evaluate this yet. This is more of a typical calculus expression. This is kind of what Archimedes started with way back thousands of years ago. This is more modern calculus. We'll work with the left side later on. Right now, we want to calculate the right side. So you just want to interpret this that the area is equal to that. When you see the dx, obviously x squared kind of pairs with that guy, right? The dx is kind of like saying the width. Okay, it's kind of that idea, all right? So we are going to take this expression and we're just going to multiply that out. So I will have the limit as n goes to infinity of the sum from I equals 1 to n of 2i squared gives me 4i squared times 2, 8i squared. Everybody see I get 8i squared on the top? What do you get in the bottom? N cubed. I have n squared times the n will be an n cubed. Now, what we want to do is notice how this expression is letting n go to infinity. But we have more than one variable here, don't we? We have limit as n goes to infinity, and we also have I, don't we? We want to factor everything out so that only an expression with I remains. And so what that's going to look like is this. The limit as n goes to infinity of, and in front we will put 8 over n cubed times the sum from I equals 1 to n of I squared. Oh boy, oh boy, oh boy. What do we get now? Okay. What this means right here is it means we're going to plug in the number 1. Don't write this down. We plug in the number 1. And then we add, what do we plug in next? 2. And you get 4. What do you plug in next? You plug in 3 and you get 9. Then you plug in 4 and you get 16. Then you plug in 5, you get 25. Like we are doing that all the way to infinity, okay? And we're like wondering, what does that add up to? It does, but it comes up with an expression to represent that. Do you guys remember when we did this at the end of last year?
Yeah.
A little bit.
Last year we did this remarkable thing. We're not going to redo it all, which is kind of crazy because the first year that I did this, the class had not yet done what we did last year. So at this point we just say pause, and we spent 3 days doing what we did at the end of last year that we came back to right this moment. It was kind of cool because they were intrigued. They were like, how does that work? This was the basis for it last year. We said 1 plus 2 plus 3 plus 4. There was that great mathematician named Frederick Gauss. And we said, how does he add that stuff up? Like, remember he got in trouble. He had to stay after class. And the teacher said, what do the numbers 1 through 100 add up to? And the answer was 5,050, right? How did he do it? 1 plus 100 is 101. And 2 plus 99 is? And how many sets of those are there? There's 50. And so he said 50, it will always be however many you have divided by 2, and it's the first one plus the last one. So it's the first one plus the last one. He said that's what they add up to all the time. Smart guy, wasn't he? And remember we proved that stuff? We were like, well, if it works for the first few cases, and then it works for case n equals k, let's prove that it's true for case n equals k plus 1. Remember we did those proofs? We called it mathematical induction, and we came up with some incredible proofs in that process. And we came up with a few formulas, namely 4 of them, that we're going to make use of during this time. Unless you want to spend 3 days and go back and reprove it all.
I'm good.
All right, so I want you to go to the very back of your notes so you can write down these 4 formulas that you're going to want to make use of. These are ones that we learned last year. I don't make you memorize these. I give them to you on your test, okay? But you're going to do 1, 2, 3, and 4, okay? So anywhere you can find space, for sure you have room on the back. We said last year that the sum from I equals 1 to n of I, so meaning we start with 1, then 2, then 3, then 4, then 5, okay, is just like Gauss told us. It's going to be equal to n times n plus 1 divided by 2.
What does n stand for in this?
However many terms you're adding up. So let's say you're adding up the numbers 1 through 50. We would take 50 times 51 and divide it by 2. This is just our starting point. Okay? Suppose we're not doing the sum of I. Suppose we're doing the sum of I squared. So that would be your perfect square. It's like 1 plus 4 plus 9 plus 16 plus 25. The question is, what do those add up to? And it turns out that those added up to n times n plus 1 times 2n plus 1, all divided by 6. Do you remember coming up with that formula?
No, one bit.
Well, there it is. Don't have to remember it. I just hope you can say, yeah, we did it. Okay? The fourth one is going to be the sum from I equals 1 to n of I cubed. So we're going to do I to the first power, I to the second, and I to the third. Turns out that I cubed ends up being n squared times n plus 1 quantity squared, all divided by 4. Which, if you recognize, is actually the second one squared, which is kind of interesting in and of itself. So what about the first one? The first one is if you're adding up a constant. Okay? So I equals 1 of a constant, and you're going to add that up n times. So I'm going to add up the number 3, okay? I'm going to add it up 5 times. 3 plus 3 plus 3 plus 3 plus 3. What did that add up to? 15, right? You just took your constant times the number of times you're adding it up, right? So we're going to take, so this is going to add to whatever the constant is times the number of times you're adding it up. That's all that means. And those are your 4 formulas. Everybody okay with those formulas? Going to have to reference them quite often, so make sure there's somewhere you can grab them on there, that they're handy, and we come back to our page and let's knock this problem off. Oh, Hannah's going to knock somebody off, sounds like, okay? A little aggressive, Hannah. I don't know where you get those ideas. So we look at the piece that we have left right now. I know that this problem seems like it's taking about 20 minutes. It's only going to take you about 4 minutes when you actually go through it yourself. This is a 3-day lesson. You should leave today a little bit confused. You should feel more confident tomorrow. On Monday, you should be ready to knock it out of the park. So we have that piece, and what we want to do is we want to substitute something in for that. Where it says substitute a known sum, that's what we do. We have the limit as n goes to infinity of 8 over n cubed times, and what do we put in place of the sum from I equals 1 to n of I squared? What do we put in that place? That one formula. Good. N times n plus 1 times 2n plus 1 all over 6. What do you notice about my new expression?
There's only one variable.
There's only one variable. We just have n. Isn't that a good news? What is the limit approaching? We've never done that before, have we? We have? We've let n go to infinity? Yeah, absolutely. That was your last test, wasn't it? Yeah, watch what happens when x goes. Oh, that's interesting. L'Hopital's rule. You could do that, couldn't you? Okay. All right, so here's what we're going to do. We're going to multiply this bad boy out. We have the limit as n goes to infinity. Now it's just basic algebra from this point forward. I notice right away, if you notice that something can reduce, go ahead. Notice that the n and the n cubed reduce. You notice that the 8 over 6 reduce. So I'm going to have 4 times n plus 1 times 2n plus 1 all over 3n squared. Now I'm going to have the limit as n goes to infinity of, let's multiply the top out. I will have n times 2n gives me 2n squared. Multiply it by the 4, 8n squared. Plus, what am I going to get in the middle? 3n times 4 is 12n. And then 1 times 1 is 1 times 4 is 4. All divided by 3n squared. You guys have solved this problem before. Recognize this. Notice that the top numerator or the top power is the same as the bottom, isn't it? So what's going to be the answer? It is going to be 8 over 3. Let's show that. We are going to factor out an n squared out of the top. Whoa, hey, come back here. We'll do that easy little step of factoring out the n squared out of the top. I have the limit as n goes to infinity of, I have an n squared times 8 plus 12 over n plus 4 over n squared. And that all sits over that 3n squared. So I want you to write it out because you want to appreciate the limit as it goes to infinity. What happens? Yeah, those approach 0. So that's what we want to see. And then we notice that the n squareds divide off, and you're left with none other than 8/3. Or in other words, 2 2/3, or 2.6 repeating. That's no estimation. That's exact. you added up the area of an infinite number of rectangles. Not 2, not 8, not 16, an infinite number. It's exactly 2 2/3. Look at your calculator, take that out. We'll show you how to check your answers today. I go into my y equals. My function was x squared. I'm going to zoom standard. And I find the area pressing second calculate, and I choose number 7, just like Alyssa told us, right, Alyssa?
Yeah.
And we integrate from 0 to what was our other bound? 2. And this could draw that area for me, and look what I get. I get 2.6 repeating.
Wow.
Take out your homework. It's one example today. I'm going to show you the problems you can try to start doing. You want to try to get one right before you leave today. You got 9 minutes. Okay?
The lower limit is 0. Yep. And the upper limit is 2. You just type it in here. Yeah.
All right, today you just want to focus on problems 1 and 2. Okay, problem number 1. Notice that the bounds are from 0 to 4 and that the function is 3x squared. So very similar to what we just did, right? You want to start at this part right here. So the first start that you want to have to your problem is you want to be able to write it out as, first, okay, here we go. First find the width and find the x values for which you evaluate the sum. Write that over on the side, okay? First figure out for the problem number 1. What's the width of each rectangle? Yep. Give me 15 seconds to think about that width and the x values where you evaluate the sum. Okay, so what was delta x? 4 over n, and what is x sub I? 4i over n. Now what you want to do is you want to write the definite integral. So you want to write this type of expression right after it, okay? So it's already written out for you, isn't it? So it says integral. So it says integral from 0 to 4 of 3x squared dx. So that's equal to, and then write what that looks like given your width and the x value which you evaluate the height. Plug in your numbers appropriately. Give you 30 seconds to do that, and then we'll let you kind of march on and see if you can get the correct answer. Okay, I should see limit as n goes to infinity of the sum from I equals 1 to n of, it is 3 times 4i over n quantity squared, and then the delta x is going to be 4 over n. Don't forget about that 3 in front. You're going to have to multiply that in the end. See what I'm saying? A lot of people forget about that 3. So go ahead, see if you can take care of the rest of the way. I'll come around and check. What's that? Because your function is 3x squared. So what you did is you took your 4i over n right there and you dumped it into there. You just placed it in terms of x. So it's 3 times that thing squared.
16 times 4.
Okay?
So we're only learning about this.
Yep, now you're just trying to calculate that.
Yeah, but you put the I squared on the other side.
Yeah, but I'm just gonna use this first.
Okay.
Do we have to write that whole thing out again? No.
Good. So there's something I'm looking for in your writing that I want to make sure I see that you have, and if you don't, then I'm going to check real quick. So 4 squared 16. 16 times 3. It's going to be 40. And then times 4 is 102. Yep, so I would write it as 3 times 64 would be 192. That's fine.
So we.
You can multiply it in the end, yep, you sure can. Good. Good. Multiply these out. So 4I over n squared times 4 over n times 3. This is correct. You can check your answer via your calculator. Good, you have the right idea. Aaron, I can't see, your hair's in the way. Good, good. So now you just substitute something over that. Substitute our known sum. Just like you substitute that guy, that's exactly what you're gonna do here. Good, you got the idea? Good, so you're doing a lot of things exactly right. Just be clear, this is 3 over 1. So it's just that on the bottom. So here's how you wanna write it, okay?
Wait, are you done?
Yeah.
Good, is that right? Good. I don't wanna get my calculator.
So you have the limit as n goes to infinity of the sum from I equals 1 to n of, and you had 192 I squared over n cubed, right? So now all you do so then you just pull this part to the front and leave the I squared there. Sir?
How important is it, like, how would we do this, like, the homework on the other one? Like, I know how to do this.
This one you're going to use your calculator.
Self-calculation.
The video, there's a formula you plug into your calculator and that will allow you to generate 200 without having to do it by hand. Yep, yeah, so there's another one that's like 50, there's another one that's like 40.
Okay.
If you get above like 10, we're not doing by hand, you're using your calculator. Okay? You're looking for this one? That one. I put it online. Let me go grab the hard copy.
I can just find it online then.
Okay. You are totally capable of doing number 2 as well. Number 2 as well. My hope is that we can do the other examples tomorrow and you'll be good to go. We can actually be more efficient with only 16 of you in class, which is good.
Make sure you post the video tomorrow so I can watch it. The competition.
Oh, yes. I was going to say, I think I posted the video yesterday.
Yeah, you did.